Hello. Today I will talk about separations for estimating large frequency moments on data streams. This is work by David Woodruff and Samson Zhou. In this talk, we'll consider the streaming model of computation, in which elements of an underlying dataset S arrive sequentially. And the goal is to use space sublinear in the size m of the input S to evaluate or approximate a given function on S. For example, if S is a set of m elements from the universe of size n, we'll let fk be the frequency of element k, which is how often it appears. Then the stream below, which consists of 1, then 1, followed by 2, then 1, then 2, and so forth, induces the frequency vector f equals 5, 3, 1, 0. This is because the element 1 appears 5 times throughout the stream, the integer 2 appears 3 times throughout the stream, the integer 3 appears once, and the integer 4 does not appear at all throughout the stream. We'll consider both arbitrary order and random order streams. In arbitrary order streams, the elements that induce f arrive sequentially in arbitrary order, which can be thought of as worst case. On the other hand, in random order streams, elements that induce f arrive in a uniformly random order, which can be thought of as average case. For example, both of the streams below induce the frequency vector f equals 5, 3, 1, 0. And so both are equally likely to appear as input to our streaming algorithm. The problem we'll consider is the FP moment estimation problem, so that we have the same frequency as before that's defined implicitly by the stream. Then we'll define FP to be the frequency moment of the vector f, so that FP is the sum of the pth powers of the coordinates of f. And the goal is to output a 1 plus epsilon approximation to FP given an accuracy parameter epsilon. This is well motivated by applications in entropy estimation and linear regression, where we want to fit a number of observations to a number of variables that we have. Now, even for constant factor approximation, it's known that this problem exhibits different behavior depending on the parameter range of p. For example, for p between 0 and 2, it's known that logarithmic space is enough for getting a constant factor approximation to p. This is due to Blazek et al. And Braverman et al. On the other hand, for p bigger than 2, it's known that polynomial space in N is necessary for FP on arbitrary order streams. This is due to Ganguly. And for random order streams, another polynomial is necessary in terms of space for frequency moment estimation. This is due to Chakrabarty et al. Moreover, we have a algorithm that computes FP with p more than 2 up to a constant factor approximation that uses space polynomial N. This works for both the arbitrary order and random order streaming model. This is due to Ganguly, Braverman et al., and Ganguly and Woodruff. But in summary, we know that this problem exhibits different behavior depending on the range of p. In particular, in this talk, we'll focus on p bigger than 2. We'll also consider a tighter estimation of FP. Namely, we'll consider 1 plus epsilon approximation for FP. Well, it's known that for such an approximation of FP, there's an algorithm that uses space 1 over epsilon to the 20 times a polynomial N, due to Braverman et al. And similarly, an algorithm that uses 1 over epsilon squared times this polynomial N, due to Ganguly and Woodruff. But this latter polynomial algorithm uses space that also has logarithmic terms in N that's omitted in this expression here. On the other hand, we know that space 1 over epsilon squared times a polynomial N is necessary for both arbitrary order streams in both insertion only and turnstile models. This is due to Ganguly. But our understanding of this problem is not quite the same for random order streams. Namely, for random order streams, our best known lower bound is the sum of a polynomial N plus 1 plus epsilon squared, so that this 1 over epsilon squared factor does not multiply this polynomial N. So it's a natural question whether this gap in our understanding is due to a lack of some understanding, or due to a separation in the characterization of the space complexities of this problem between these two different models. Our results for FP moment estimation with p bigger than 2 is firstly an algorithm for random order insertion only streams that uses space 1 over epsilon to the 4 over p times the polynomial n, and a same space algorithm for 2-pass streams in arbitrary order, even with turnstile updates. We also show a lower bound of 1 over epsilon squared times a polynomial n, that this is necessary for 1-pass arbitrary order streams. And thus our results show a separation between 1-pass arbitrary order and both 1-pass random order and multi-pass arbitrary order. In summary, our results show that by considering random order streams instead of arbitrary order streams, we can improve on a large line of active work. And we also show an improved lower bound for arbitrary order streams upon existing work. So our upper bound will crucially rely on the concept of level sets, which I'll define now. Consider a partition of the coordinates k into level sets lambda I, based on the frequencies of each item, so that k is in lambda I if the pth power, the frequency of k, satisfies a certain bound. Then we'll define the contribution ci of the level set lambda I as the total contribution of all coordinates in the level set to fp, so that ci is the sum of the pth powers of the frequencies of k for the coordinates k that are in the level set lambda I. The intuition is that the level sets decompose fp, so that if we write fp as the sum of the pth powers of the coordinates of f, we can write this further as a double sum, where the inner sum is distributed over the level sets lambda I. But now we can write this inner term as just the contribution of each level set, so that fp is just the sum of the contributions of each level set. Thus, to obtain a 1 plus epsilon approximation to fp, it suffices to obtain a 1 plus epsilon approximation to the contribution of each level set. To get an accurate approximation to the contribution of each level set, we'll first consider the definition of heavy hitters and show how a reduction follows. The heavy hitter problem is defined as follows. Suppose we have the frequency vector defined as such in the previous slides by the updates to the stream. Then we'll let LP be the norm of the frequency vector, which is equal to the frequency moment FP raised to the 1 over P power. Then the goal is to output the elements K, whose frequency exceeds epsilon times LP, given in a threshold parameter epsilon, and we want an approximate frequency to each of their actual frequencies. The heavy hitter problem is well motivated by applications in distributed denial of service attacks and identifying iceberg queries in databases, so it's well studied and has a long line of active work that we'll gladly utilize. So how does this reduction from heavy hitters to level set contributions work? Well, if the pth power of the frequency exceeds an epsilon squared fraction of the fp, then we know that the frequency exceeds epsilon to the 2 over p times lp, which implies that k is an L2 heavy hitter with threshold epsilon to the 2 over p divided by a polynomial in n. Thus, we can use an L2 heavy hitter algorithm with threshold epsilon to the 2 over p over a polynomial in n to find k and obtain an approximate frequency fk. Now recall, to obtain a 1 plus epsilon approximation to fp, it suffices to obtain such an approximation to the contribution of each level set. Now we know that if the pth power of the frequency of k is sufficiently large, then an L2 heavy hitter algorithm will be able to identify the coordinate k and obtain an approximate frequency. Moreover, if the estimated frequency is a 1 plus epsilon approximation to fk for all such k, then we obtain a 1 plus epsilon approximation to the contribution of the level set. In summary, we obtain a 1 plus epsilon approximation to the contribution of each level set lambda I, where lambda is less than log 1 over epsilon squared. And this restriction on I comes from the assumption that the pth power of the frequency of k exceeds epsilon squared times fp. Okay, so that handles the level sets with large frequencies. And so it remains to consider the level sets with small frequencies. Namely, we want to approximate the contribution Ci of each level set lambda I with I larger than log 1 over epsilon squared. Now, as a case study, let's first suppose that the contribution is equal to fp for some I larger than t, where t is equal to log 1 over epsilon squared. Since the frequency of k for each k in the level set satisfies a certain range, then we know that the size of the level set, namely the number of coordinates in this level set lambda I, has to exceed 1 over 2 to the 2 to the I minus 1. Thus, if we sample the universe at a rate 1 over 2 to the I minus t, then in expectation, at least 1 over epsilon squared elements of lambda I will be sampled. And the intuition is that if we have approximate frequencies to these items that are sampled, then we can use them to estimate the contribution Ci. Namely, we show that a standard variance argument proves that rescaling the sampled contribution by 2 to the I minus t gives a 1 plus epsilon approximation to the contribution, provided that we sample 1 over epsilon squared elements of lambda I. Now the question is, how do we compute these approximate frequencies? Well, we note that if we sample the universe at the rate 1 over 2 to the I minus t, then the frequency moment of the subsampled stream will be a 1 over 2 to the I minus t fraction of the original frequency moment in expectation. Thus, we expect the frequency of k to be a heavy hitter with respect to the subsampled stream. Hence, we can use the same argument as before. Namely, we use an L2 heavy hitter algorithm with threshold epsilon to the 2 over p divided by a polynomial n with respect to the subsampled stream. Then we can use that to find k and obtain an approximate frequency to fk. In summary, if Ci is equal to fp, then an L2 heavy hitter algorithm on a substream that samples k with rate 1 over 2 to the I minus k and a certain threshold can obtain an approximate frequency to fk. Moreover, if this approximate frequency is pretty accurate, like up to a 1 plus epsilon approximation, then we can rescale and obtain roughly a 1 plus epsilon approximation to the contribution. Now recall again that to obtain a good approximation to fp, it suffices to obtain good approximations to the contribution of each level set. And the previous argument shows that we can obtain 1 plus epsilon approximations to the contribution if the contribution of a level set is equal to fp. But more generally, the same argument will work if the contribution is equal to gamma I times fp for some gamma I between epsilon and 1. This is because we'll actually get a 1 plus epsilon over gamma I approximation to the contribution, which translates to at most an epsilon times fp additive error to the contribution. So the idealized algorithm is as follows. We'll first form log n streams, S0, S1, S2, and so forth, by subsampling the universe, n, at a rate 1 over 2 to the j for each of the substreams. Then we'll use an L2 heavy hitter algorithm with a specified threshold of epsilon to the 2 over p divided by a polynomial n on each of the substreams. And these algorithms will output 1 plus epsilon approximate frequencies to each reported heavy hitter. We'll use these approximate frequencies to compute approximate contributions for each of the level sets. Then we'll output the sum of the contributions, and that will form our estimate to the FP of the stream. So the space of our algorithm is heavily dominated by the L2 heavy hitter algorithms that use threshold epsilon to the 2 over p divided by a polynomial n on each of the substreams. We can black box heavy hitter algorithms for one-pass random order insertion only streams and two-pass arbitrary order turnstile streams, but similar results are not known for one-pass arbitrary order insertion only streams. So these heavy hitter algorithms that we'll utilize are: first, there exists a two-pass algorithm count sketch that finds the exact frequencies of the L2 heavy hitter algorithms with threshold epsilon, and it count sketch uses space 1 over epsilon squared times log squared n on arbitrary order turnstile streams. For random order streams, we'll use a one-pass algorithm count heavy hitters that finds a 1 plus epsilon approximate frequency, and it uses space, again, roughly 1 over epsilon squared times log squared n. So these algorithms use space roughly 1 over epsilon squared for threshold epsilon, but we require threshold epsilon to the 2 over p divided by polynomial n, which gives our resulting space of 1 over epsilon to the 4 over p times n to the 1 minus 2 over p. And this space complexity shows a separation between one-pass arbitrary order and both the one-pass random order and multi-pass arbitrary order, this FP moment estimation problem. Now, the source of the separation is the ability for heavy hitter algorithms to find 1 plus epsilon approximate frequencies of the L2 heavy hitters using threshold epsilon in space 1 over epsilon squared. There are algorithms that can do this in the one-pass random order insertion only streams and two-pass arbitrary order turnstile streams, but such an algorithm is not known for one-pass arbitrary order insertion only streams. So that wraps up our upper bound. And for the remainder of the talk, we'll discuss the lower bound that we show of space 1 over epsilon squared times n to the 1 minus 2 over p for one-pass arbitrary order streams. Our lower bound works as follows. We first define the T epsilon n player set disjointness problem, and we show that this problem has total communication cost n over t. Then we set T to be roughly 1 over epsilon times n to the 1 over p, and we show a reduction from 1 plus epsilon approximation of fp to this T epsilon n player set disjointness problem. So in this problem that we define, there are t plus 1 players, p1, p2, all the way to p t plus 1. Each of the first t players receives a vector that has dimension n and is binary. But the last player receives a spike location, this is j, and a bit c that is either 0 or 1. Now, if we let u be the sum of the vectors that each player receives, the promise is that ui is at most 1 for each I that's not equal to the spike location, and either uj is at most 1 or uj is equal to t. Intuitively, these conditions correspond to the first condition that the player sets are disjoint outside of the spike location j, and at the spike location j, either the player sets are entirely disjoint or they all have j in their sets. Now, the last player must differentiate between the three cases that are listed below. The intuition is that since the first t players do not know the spike location, then they must solve the problem on all coordinates. But solving multi-party set disjointness on a single coordinate is roughly equivalent to solving the and of t bits. And a standard Hellinger distance argument shows that the information complexity of and is roughly 1 over t for t players. Thus, we can use a direct sum embedding to show that the total communication cost of this T epsilon n set disjointness problem has communication cost n over t. Now, the reduction works as follows. So recall that the problem is defined so that for each of the first t players, they receive a binary vector of length n, and the last player receives a spike location in a bit. Then the first t players inserts the coordinates of their vectors into the stream. And the last player creates a vector that depends on both the spike coordinate, the spike location, and the bit C. And they also insert the vector that they create into the stream. The intuition is that because most of the coordinates of the players are disjoint, then the mass added to the spike location provides a separation for FP depending on the different cases, whether the spike location has disjoint coordinates across the players. Namely, we show that if C equals 0, then the FP of X is small. But if C equals 1 and the spike location is roughly disjoint, then the FP moment of the vector X is roughly medium. And finally, if C equals 1 and all players have the coordinate T in their sets, then the FP moment of X is large. And thus, 1 plus epsilon approximation of FP separates these three cases and solves the set disjointness problem for T roughly equal to 1 over epsilon times n to the 1 over p. Hence, a 1 plus epsilon approximation of FP requires a space of 1 over epsilon squared times n to the 1 minus 2 over p. And this proves our lower. In summary, our work shows both improved upper and lower bounds for random order streams and arbitrary order streams. For random order streams, we first show an upper bound of 1 over epsilon to the 4 over p times n to the 1 minus 2 over p. And we show roughly the same space complexity for two past streams in arbitrary order, even with turnstile updates. On the flip side, we show that the 1 over epsilon squared times n to the 1 minus 2 over p is necessary for one past arbitrary order streams. Thus, our results show a separation between one past arbitrary order streams and both one past random order and multi-pass arbitrary order streams. For more information, I defer to our paper, and thank you for taking the time to listen to our talk.